So we're looking today at AS Physics, CCEA 2024, and it's Unit 2, Waves, Photons and Astronomy. Let's get started. Question 1a. The first column of Table 1.1 shows 4 properties of waves. Place a tick in each row to indicate if the property applies to sound waves, electromagnetic waves, or both. So firstly, we've got transfer energy. Now, that's one of the basic properties of waves. It's not specific to either sound waves or electromagnetic waves, so that counts as both. Can be refracted. Again, refraction is an example of a basic wave property, so again, that would apply to both. Can be polarized. So if you remember, polarization is a wave property that only applies to transverse waves. And since sound waves are longitudinal, then we would only be able to take electromagnetic because all electromagnetic waves are transverse. Require a medium to travel through. Okay, so that's mechanical waves require a medium, a solid, liquid, gas, etc. And that does apply to sound waves, but it doesn't apply to electromagnetic waves because obviously we can see the stars through the vacuum of space. Electromagnetics, that's one of their key, unique properties, that they can travel through a vacuum. So they don't require a medium, but sound waves do. Part B then. A wave of frequency 6 Hz travels at a speed of 2.5 kilometers per second. Calculate the wavelength of the wave. Okay, so this is a straightforward use of your wave equation with the slight complication of having to convert one of the units. Hertz are fine, but kilometers per second is not a suitable unit. So our 2.5 kilometers per second can be written as 2,500 meters per second. So if V equals F lambda, then lambda is just going to be V over F, and we substitute now in our V and our frequency. And 2,500 over 6 comes to 420 meters. So you probably noticed that this comes out to be 416 points repeating 6, but our original question numbers are to 2 significant figures, so we should really quote this to 2 significant figures, which would mean we write it as 420. Part 2, calculate the phase difference between 2 points on the wave that are 50 meters apart. State the unit of phase difference. So we have a lambda wavelength here of 420 meters, and we've got 2 points 50 meters apart. So we want to find that point difference, 50 meters, as a fraction of the 420. And then we could convert it to degrees by multiplying that by 360. You could also multiply it by 2 pi if you wanted the answer in radians, but we'll do degrees. And that comes to 43 degrees. And again, we're still working to 2 significant figures because of the original input numbers being in that form. Question 2. Water waves created in a ripple tank can be used to demonstrate some of the properties of waves. And figure 2.1 shows a ripple tank set up to create waves. And you can see the setup here. They've got a power supply, they've got a long paddle that's oscillating, and that's creating nice flat waves. Ripple tank contains a shallow tray, water, transparent base, light source directly above, and white screen beneath the tray. The oscillating paddle creates waves that move across the tray and shadows formed by the waves show up on the white screen. Part A, figure 2.2 shows the wavefronts in a ripple tank approaching a gap in a barrier to demonstrate diffraction. Draw 4 wavefronts to show what happens to the water waves as they pass through the gap in the barrier. So there's things that we need to be consistent about. For example, the wavelength shouldn't change. We've got a gap here that is bigger than the wavelength. So there's certain features that we should show. So first of all, there will be a straight section and you're going to want to try and keep that the same wavelength as before. And then at the edge of these, you're going to have curves coming round, again keeping the wavelength consistent, not going all the way to the barrier. So a straight bit in the middle and curves at the edges. Again, you might want to bring that around a little bit more. So, it says the gap is now adjusted so that it is 1/3 of its previous width. So that's going to be much closer to the wavelength. State what will happen to the amount of diffraction and explain your answer. And those are your 2 facts basically. The amount of diffraction we would expect to increase, and it's because we've got closer to, the gap is now closer to the wavelength. Part B. In another demonstration, the wavefronts appear as shown in figure 2.3. Describe what happens to the wavelength, speed and direction of the waves after passing into the region beyond the line AB. So what's happening to wavelength, what's happening to speed, and what's happening to direction. So wavelength is definitely getting smaller here. These are definitely bigger gaps and these are smaller gaps. Speed always follows what wavelength does, remember, in waves. So if wavelength gets smaller, then speed will also get smaller, so speed reduces. And these two are what happens when light goes from a more dense to a less dense material normally. In the case of waves, it's like deep water to shallow water. And when light slows down, it always bends towards the normal. So follow what has happened. The waves have slowed down, so they're bending towards the normal. What property of the waves is this demonstrating? Well, this is clearly refraction, because we've got a change of speed. The Nobel Prize in Physics in 1921 was awarded to Albert Einstein for his services to theoretical physics and especially for his discovery of the law of photoelectric effect. Explain what is meant by photoelectric effect. So in photoelectric emission you have photoelectrons, which are basically electrons, but we call them photoelectrons because of how they're being created or emitted in this particular case. So we have photoelectrons emitted from a metal surface when the metal surface is irradiated by electromagnetic radiation above a certain value of frequency. Part 2 then, describe the observations that led Einstein to use the photon model to explain the photoelectric effect. So the most Important thing about photoelectric effect is that if your illuminating radiation goes down below this threshold frequency, then all photo emission stops. The other thing is that, it doesn't take time for the energy to build up in the material, that the photons the photons cause photoelectrons to be emitted immediately. So the minute you would uncover the light source, you should start to see photoelectrons immediately. So there's no energy building up in the material. It's an instant process. As you increase the frequency, you will also get the remaining kinetic energy, like what's left over from the interaction between the photon and the metal. The kinetic energy of the outgoing photoelectrons increases as you add on frequency to your illuminating radiation. And if you increase the intensity of the light, then you should see an increase in the number of photoelectrons emitted. So that first one's the most important observation. So the idea that it happens instantly. So we get more kinetic energy in the photoelectrons if we raise the illuminating frequency further. So again, when we turn the brightness up, once we're above the threshold, if we turn the brightness up, we get more photoelectrons. But below the threshold, it wouldn't matter what we turned the brightness to. So if you imagine red was below the threshold and violet light was above, no brightness of red light would create photoelectrons. Part B, calculate the energy in electron volts of a photon of electromagnetic radiation of frequency 2.97 times 10 to the 14 hertz. Okay, so it's sort of a units thing and an equation thing. So we have the energy of a photon related to frequency is E equals hf. So h is your Planck's constant and frequency is that value they've just given us. Planck's constant can come from your formula sheet and a value of 6.63 times 10 to the minus 34, and then we multiply by that value of f. Multiplying those together, we get a value of 1.97 times 10 to the minus 19. Again, we're operating to three standard figures because that's what the input numbers are doing. So we still have a conversion to electron volts to do by dividing by the elementary charge. 1.6 times 10 to the minus 19, the charge of an electron. And doing that will give us a value of 1.23 electron volts, again to three standard figures so that we're matching the numbers coming in. Part 2 then, this radiation is shown on a metal with a threshold frequency of this value of hertz. Calculate the maximum velocity of an emitted electron. So remember, what goes on in photoelectric emission is that the photon has an energy, the metal takes the work function energy, and whatever's left over can become the energy left over to be kinetic energy. And so the fastest emitted photoelectrons will have left with all of their kinetic energy, and that's why they talk about it being the maximum velocity. Only the fastest ones get away with all the energy that's left over from the interaction. So the leftover energy to become kinetic equals the photon energy hf minus the threshold energy hf naught. So we multiply both sides by 2, divide by m, and then take the square root. That'll get us V max. Or you could work all these terms out separately and just fiddle around with them as after you've substituted. But I'm going to try and substitute in one go here. So we've got a square root of HF minus HF naught. Now to simplify this substitution, I'll calculate HF naught over on the left hand side here. Okay, and I'm getting 1.6 times 10 to the minus 19 joules for that, so I'm going to sub that in. And we're dividing all of that by the mass of an electron, which you'll get again from your formula sheet. And that's what I'm getting for that, so like 2.85 times 10 to the 5 meters per second. Part 3. Why are other electrons released with a range of velocities lower than this? And so this is the idea that they all initially are handed the same kinetic energy, but not all of them manage to make it to the surface of the metal with all of that intact. Okay, something explaining that they need energy to get to the surface. So the ones we're going to be getting that maximum value for are ones that were released at the surface and immediately were able to leave with all their kinetic energy. 4a, describe the difference between cosmological redshift and Doppler redshift. So regular old Doppler redshift is when the source is moving away from you, and cosmological redshift gives the extra complication that the space between the source and the observer is actually stretching. So you need to describe that difference. Part B. The red line emitted by hydrogen discharge tube in the laboratory has a wavelength of 656.3 nanometers. The same line in the hydrogen spectrum of a moving star has a wavelength of 716.5 nanometers. Explain how it can be concluded that the star is moving away from Earth. So we've got clearly a longer wavelength in the moving star. So the moving star has a wavelength that is longer. That is a redshift, and that means it's moving away. So you need to go through a sort of an argument about what's happening there. Calculate the speed at which the star is moving away from Earth. So remember, we have an equation that says that the fraction of change in the lambda equals the fraction of the speed of light that this object is moving at. So delta lambda over lambda is V over C. So V is going to be delta lambda times C over lambda. And substituting into that, so the difference between the two lambdas, remembering that these are times 10 to the minus 9, is our delta lambda. We're multiplying that by 3 times 10 to the 8 for C, and dividing by the actual lambda, we should get a value for V. And I forgot my 10 to the minus 9 here, so I need to fix that. And when you substitute in, I'm getting that, which would be like 2.75 times 10 to the 7 meters per second. Question 5, Part A. In an experiment to measure the critical angle of glass, a ray of light is directed towards the centre of the flat surface of a semicircular glass block as shown. Describe what will happen to the ray of light at the flat surface of the glass block when the ray of light is at position A and is moved from position A to a point just before position B. So we're starting here and then we're moving round to there. So remember with the semicircular glass block that because you're aiming at the middle here, you're always coming in along a radius, and therefore you're always crossing this initial curved surface. You're always hitting it along a normal, and so there's no bending as long as you're aiming at the middle of this, then you're always going to come in here at 90 degrees to the surface, so you're running along a normal all the time. So we're asked to describe what will happen to the ray at the flat surface of the glass when we move from incident ray at this position to incident ray all the way down here. So at position A here, we're coming in along a normal to this surface, and we're coming in along a normal to this surface. So the ray will keep going and leave along the normal to the surface. As we start to get into these steeper positions here, then what you'll find is that we have no change of direction at the curve. So we're not really interested in that because they only want to know what happens at the flat surface. But obviously it's going to speed up as it exits the glass, and so it's going to bend away from the normal. So you want to give a description of what happens at the very beginning, which is the two interfaces. The ray is at the normal, so it will exit along the normal. Then you want to talk about there being, because it's speeding up as it leaves the glass, there'll be a bending away from the normal. You should also start to see some partial reflection, because every interaction with the surface can give rise to reflections. But that reflection will increase in brightness as the angle of incidence approaches the critical angle, and then beyond the critical angle you'll only see the reflected light. You'll only see what we call total internal reflection, with no light emerging at the back surface anymore. The critical angle is found to be 44 degrees. Calculate the refractive index of the glass. So this again use of your equation. So n is 1 over sine c. So we sub into that with c of 44 degrees, and that gives us an n of 1.44. Part B, optical fibers are used to transmit information over long distances. Each fiber consists of a core of glass A coated with a layer of glass B, as shown in figure 5.2. Which glass, A or B, has the higher refractive index? And explain your answer. Right, remember what we need to have, the conditions for total internal reflection, is that you have to be greater than the critical angle here, and you have to be trying to go from a more dense to a less dense medium, or you cannot have total internal reflection. So that means that we have to have a more dense here, less dense here, and so the higher refractive index has to be in the core. So remember that we have conditions for total internal reflection, and therefore we can explain then that it must be starting in the higher refractive index, which means that A must be the higher refractive index. Part C. Impurities in the glass used to make an optical fibre reduce the power transmitted by 20% for every kilometre. The power of light entering the fibre is 175 watts. Calculate the power of light when it has travelled through 4 kilometres in the fibre. So 20% lost is like 80% remaining. So for each kilometre, you're going to have a factor of 0.8 remaining each time, and it's probably easier to do it that way rather than to be subtracting 0.2 and then subtracting another 0.2, because if it keeps the 0.8 and you just multiply by that factor 4 times, that should give you what you're left with. So with 80% remaining after the first kilometre, and then 80% of that after the second kilometre, and then 80% of that after the third kilometre, and 80% of that after the fourth kilometre, this should give us how much is left after 4 kilometres. And I get 71.68, which to 3 significant figures, because they start with 175, which is 3 significant figures, 3SF, that should be 71.7. Question 6. In an experiment to measure the wavelength of light from a laser, The light from the laser was directed along a normal onto a diffraction grating with 600 lines per millimetre. A diffraction pattern consisting of bright spots was observed on a wall 2.5 metres from the diffraction grating, and the central bright spot and the first two spots on each side are shown in figure 6.11, and they've given us the distance to those between those second spots on either side. Calculate the wavelength of the light coming from the laser. So if you imagine your source is here, then this is the line going to the central, and then there's a line going to this one, and there's information we can get. Now we're interested in that angle there. Okay, so we can get that angle from the tan because this opposite side is going to be half of 3.52, which is going to be 1.76. And we've already been told that the distance to the wall is 2.5 metres, which means obviously this triangle is not to scale because 2.5 is definitely more than 1.76, but they didn't leave us enough room to draw a proper triangle, but it'll be fine. So the tan of theta is opposite over adjacent, which is going to be 1.76 over 2.50, so we can get theta from that. So theta is going to be tan to the minus 1 of 1.76 over 2.5. So theta equals 35 degrees, and we can feed that into our equation. So we have d sine theta is n lambda. D is the fringe or the spacing on the lines on the diffraction grating. Theta is the angle we're measuring out to. N is which order of maxima we're measuring out to, and so n here is the second dot out from the centre, so it will be n equal to 2. And d, we were told that the diffraction grating was 600 lines per millimetre, so if we divide 1 millimetre into 600 gaps, we'll get the value of d. And so all the numbers are known. So d is 1 times 10 to the minus 3, 1 millimetre, divided by 600, which is 1.67 times 10 to the minus 6. So we should be ready to substitute after rearranging this equation for lambda. So lambda is going to be d sine theta over n. So now we just sub in what we know. So we had this value for d, we had 35 for theta, and we had an n of 2 because we're at the first second, okay, maxima there. And so that should give us lambda. So that's lambda in meters. And we're going to want that in probably nanometers. Okay, no, they want it in meters, so that's fine. Just bring it back to 3 significant figures, so 4.79 or times 10 to the minus 7. So again, summarising, use what they've told you about the grating to get the value for d. 600 lines per millimetre, so 1 millimetre divided into 600 is the width of one of those gaps. Use the diagram and the idea of tan to get the opposite and the adjacent to the theta that we're interested in. Once you've got that theta, once you've got that d, you should be able to just substitute into the equation from that point. Part B, what effect does each of the following changes have on the spacing of the bright spots formed if all other factors are kept the same? So using light of a longer wavelength. So if you keep everything else the same, then the spacing is going to come from what happens to theta when you make those changes. So we've got d sine theta equals n lambda, and the angles here, because of the shape of the diagram, are all between 0 and 90. Now we know that what happens to the sine of theta between 0 and 90 is it starts at 0 and it gradually increases to 1. Now it's not linear, but it always is increasing on the way up to 90. So if we get sine theta on its own, then we're effectively getting theta on its own. in terms of increasing. So sine theta would equal n lambda over d. So what we've got here is, because there's a lambda on the top line, increasing lambda will increase theta. So the spacing should increase. But if we have fewer lines per millimeter, then that would increase d. The gap between them would get bigger. If you had fewer lines per millimeter, then the gaps themselves would get bigger. So increasing lambda will make the dots get further apart. The spacing of the dots will increase. Increasing or decreasing lines per millimeter will increase d, and that will reduce the gap between the spots. So if you have a bigger lambda, we should see the spacing increase. That second change would cause a bigger d, and that would cause the spacing to decrease. Question 7. Noise-cancelling headphones have a microphone that picks up an incoming sound wave. A speaker then produces another sound wave which causes it and the incoming sound wave to destructively interfere and cancel each other out. State the general conditions that are required for complete destructive interference. Okay, so remember that to get destructive interference, you have to have peaks from one meeting troughs from the other. So they effectively have to be in an antiphase. And for the sizes of them to be the same, and you can get full cancelling if the amplitudes are equal. So you've got an antiphase, but it's an equal amplitude in order to get complete cancelling. Okay, part 2. The noise cancelling is not perfect because there is a slight time delay between the incoming wave and the wave that is produced. In one set of headphones, this delay is 1 millisecond. Figure 7.1 shows the incoming wave. Draw the wave produced by the speaker in the headphones. Okay, so we're looking for a 1 millisecond delay. And it's also going to need to be inverted. So 1 millisecond delay means that it's going to be starting here. It's going to reach a negative peak of 2 squares 1 millisecond after the other one reaches its peak. It's going to go back to 0 1 millisecond after the other one goes back to 0, and it's going to exit. Again, it's going to follow that pattern of being 1 millisecond out. So we're going to have something that follows these dots. So something along those lines. Part B. Figure 7.2 represents a standing wave with a pipe closed at one end. The length of the pipe is 60 centimeters. What is the name given to the points on the wave labeled Q, R, and S? Okay, so we know that those are called nodes. And then it says calculate the wavelength of the standing wave. Okay, so it's easy for us to use our highlighter to sort of say, how many waves we've got here. You can see if I follow through. Oh, that's a black highlighter. Give me a second, sorry. If I follow through here, we get one wave and like a quarter. So it's 1 1/4 lambda equals 60 centimeters. Okay. So 1 1/4 lambdas equals 60 centimeters, which also equals 0.6 of a meter, but we can work it out in centimeters first. So lambda is going to be 60 over 1.25, which is 48 centimeters. So we're looking for 0.48 of a meter. Calculate the longest wavelength of a sound that can be produced, that can produce a standing wave in that pipe. So if you think about the fundamental with a node and an antinode, that's the most simple system that you can form in that pipe. And that would look like this. So in this position we only have a quarter of a wave, and that's equal to 60 centimeters. So lambda over 4 equals 60 centimeters, and lambda double equals 60 times 4. So that's 240 centimeters, which would be 2.4 meters. So remember, what's going on here is they ask for the longest wavelength. So as we increase the wavelength, eventually we'll get the shortest thing that will actually fit. And the shortest thing that will fit is a fundamental, where you have a node at this end and the first antinode at that end, which means you've only got a quarter of a wave, which means we can write this equation, which means we can figure out what lambda is. So remember that a quarter of a wave is the idea that, if a wave looks like this, then by the time we reach this point, we've only gone to this first peak, which is why we say it's a quarter of a wave. And then the rest follows from the idea that lambda over 4 now equals 60 centimeters. Question 8a. State two differences between the properties of white light and laser light. So, what properties does white light have? Well, it's got a mixture of colours, whereas laser is what we call monochromatic. It only contains one colour. Okay, so white light has many colours, whereas the laser is monochromatic. Laser is also what we would call a coherent source, so everything's in phase, whereas white light doesn't have to be. It can't really be because it's got a mixture of wavelengths. Part B, describe how laser light is produced, explaining any of the terms you use in your answer. So we obviously have a big long description here of what's happening with electrons in the active material in the laser. So you've got energy from an external source going into electrons in the active material of the laser. Those electrons move to higher energy levels. They eventually fall back down and get built up in a metastable state, explaining that a metastable state is a state with a longer lifetime. You eventually get more in the metastable state that are in the ground state, and we call that population inversion. Eventually you get some kind of emission. Then you get like stimulated emission, because the photon has the same frequency as the ones produced by all the ones that are currently sitting in the metastable state. And then you get a lot more stimulated emission as the wave travels up and down. Okay, so you've got some energy being input to the system. There has to be something driving the electrons up to the higher levels. And then they settle back to this long-lived state that we call a metastable state. So then you want to talk about population inversion. So we then describe the formation of a population inversion, where you have far more electrons in the metastable state than in the ground state. So when electrons start to spontaneously emit from the metastable state, those photons that they produce will pass other atoms stuck in the metastable state and cause them to produce a stimulated emission. So it's the uniqueness of the photons that have this property, that they can stimulate emission from other electrons that are in the same state that their electron used to be in. And the other thing is that they emit in perfect phase, which is why we've got a coherent source in the laser. Question 9. A small upright object is placed in front of a screen, and then a lens is placed between the object and the screen. The lens is moved until a focused image is formed on the screen. The position of the object and the screen and the image are shown in figure 9.1. Name the type of lens used to form this image. it's a real image, so it would have to be a converging lens. On figure 9.1, draw construction rays to find the position of the lens and the position of the principal focus. Draw the lens in the correct position using the correct symbol and label the principal focus F. So this all comes about from the idea that any rays leaving this object must converge to this point. Now we know there's a ray that runs through the optical center, so if we join here to here, we should get the optical center of the lens. Equally, if we run parallel until we get to the lens and then we turn and arrive here, we should have gone through the focal point, principal focus value on that same location as it crosses the axis. So that's what we want to look at. But yeah, first of all, this is a converging lens. So we need a straight line tool here. You get a ruler, but I'm going to get a straight line tool and see if I can draw from one of these positions to the other using a straight line tool. So a line from the top of the object to the top of the image will have gone through the optical center. So that lets us know where the lens is. So we can now add in our lens. So the lens would appear to be here, and it's a converging lens, so we put outward facing arrows like that. And now we want to see where a ray running parallel to the axis, it also then has to arrive at the image. So this ray has to also arrive here, but on its way through the axis it'll pass through the focal point, the principal focus, so we need to complete that. And that will help us locate the principal focus here. And that's it, that's what they asked us to do. Part B, use measurements from 9.1 to calculate the magnification. Okay, so we need the image size and object size to get magnification, height of the image, height of the object. So we should measure those from the diagram. So with an object height of 3 and an image height of 1.6, we've got M, the magnification, is HI over HO. Subbing that in, we get a magnification of 0.53. Part 2, explain why the ray diagram does not need to be drawn to full scale to get the correct magnification. Yes, because it doesn't matter what the actual units are, it's just the ratio of those two values, therefore it doesn't matter what they're being measured in, as long as it's consistent. Okay, so it's just a ratio, so the scale doesn't really matter. C, part 1. Lenses are used to correct defects in sight. State the name of one defect that can be corrected by a lens. Identify the cause of the defect and type the lens used to correct it. Okay, so for myopia, this is someone who can see close things, they just can't see far away things. And so when they try and look at far away things, their lens converges the rays too much and they meet before the retina. You could also argue that the eyeball itself is too long. That's also why they meet before the retina. And you correct that using a diverging lens. I'm just clarifying here that lens is too strong, eyeball too long to see far objects. Okay, so hypermetropia, the lens is like too weak to see close objects. So the lens is too weak or the eyeball is too short. Again, this time it's to see close objects. And you should probably use the phrase see clearly or focus. Be careful about that because you can definitely still see a blurry thing. It doesn't mean you don't see it, it's just not sharp. And obviously a converging lens will help you with that because it'll help to make the overall strength of your vision system stronger. So, complete both parts of figure 9.2 to show how the lens works to correct the defect you have chosen in C1. So it depends what you've chosen. So let's say we've chosen myopia. So someone with myopia struggles to see a far object, and it's because the lens is too strong. And so the rays converge before the retina and therefore don't form a sharp object. So if we add in a diverging lens, so the rays diverge a little before entering the eye, and then it does the rest of the bit of converging them to a sharp point on the retina. Two lenses are compared. Lens A has a power of plus 3D and B has a power of minus 2 diopter. Describe two differences between the lenses. Okay, so one is a positive power and one is a negative power. So one is a converging, the positive one is a converging lens and the negative one is a diverging lens. And secondly, the converging lens is more powerful than the diverging lens because it's got a bigger power. So a bigger power will correspond to a shorter focal length. So the more powerful lens would also have a shorter focal length. You could say it that way if you wanted. So A has a shorter focal length than B. And that's that. Okay, thanks for watching. Hope you got something out of that. See you next time.